approximation in quantum mechanics that assumes the wave functions of electrons and the atomic nuclei in a molecule can be treated separately. This approximation is basically based on the fact that the mass of an atomic nucleus is much larger than the mass of the electron. So the nuclei move much more slowly than that of the electrons. This Oppenheimer approximation in quantum mechanics, quantum chemistry, and molecular physics, this approximation is best known mathematical approximation in molecular dynamics. Especially, it is the assumption that the wave function of the atomic nuclei and electron in a molecule can be treated separately. Based on the fact that the nuclei are much heavier, much massive than that of the electrons. And due to the larger relative mass of the nucleus compared to the electrons, the coordinates of the nuclei in a system are approximated as fixed, while the coordinates of the electrons are chosen dynamical. The approach is named after Max Born and his 23-year-old graduate student Oppenheimer. And this approximation is widely used in quantum chemistry, especially just to speed up the computation of molecular wave functions and other properties of larger molecules. Certainly, there are cases where the assumption of separable motion no longer holds, which make the approximation lose validity. But even then, the approximation is usually used as a starting point for more refined methods. This Oppenheimer approximation makes it possible, at least, to separate the motion of the electrons and the motion of the nuclei, and it certainly forms the basis for most electronic structure methods. This approximation involves the assumptions that I'll try to confine them here. I mean, the electronic wave function, it depends upon the nuclear position, but not upon their velocities. The nuclear motion is so much slower than electron motion that they can be considered to be at rest, they can be considered to be fixed. And the nuclear motion, for example, if you take into account rotation, vibration, they see a smeared out potential from the electrons. And this Born approximation is widely used. It's used in most of the domains of molecular physics. And at the same time, this approximation breaks down when we consider two or more excited electronic states, which are energetically close or have eligible non-adiabatic coupling at some points. I hope everybody is fine, and here we are going to start with molecules, and Born approximation is one of the fundamental approximations that's utilized, that's exonerated on molecules. And in this video, I'll be talking about adiabatic approximation, and what we have is we have molecule, and molecules have atoms in them, and atoms have nuclei and electrons. So this Born approximation is probably the most fundamental approximation, both in the field of physics and more exhaustively it's used in chemistry. Now from practical point of view, what it does is it allows us to treat the electronic structure of molecule very accurately without worrying too much about the nucleus. So if we have electronic distribution and the nucleuses, so So anytime we find a physicist or a chemist trying to draw a picture like the one that we have been talking about. And what is important here is that we are implicitly making use of the framework that's suggested by Bohm and Oppenheimer. So Oppenheimer approximation. So let's go with this approximation. Now, if we have a molecule, and what we are going to do here in this case, as long as we have to discuss adiabatic approximation, in this approximation, we will choose our Hamiltonian in atomic units. And how do we choose it? We understand for that this H cross is taken equal to the mass of the electron, is taken equal to the charge of an electron, is taken equal to 1. And we can write down the Hamiltonian for a molecule, and if I write down the Hamiltonian operator, so I'll have minus 1 by 2 sigma, say delta J square by mj. Now let me use for nucleus, let me use J, and then minus 1 by 2 sigma delta I square, and plus 1 by 2 sigma z I and zj divide by r I j, then plus 1 by 2 sigma 1 by r I j minus sigma zj by ri minus rj. Now we have come across some terms over here. So the very first term, what's important here is that we have chosen our fundamental, the basic constants. We have chosen them equal to 1, and the first term here, this is the nuclear kinetic energy. So this is our nuclear kinetic energy, and so this is valid for nuclei. And then the second term that we have is the electronic kinetic energy. So this term reflects the electronic kinetic energy, the kinetic energy linked to the electrons that are present in the molecule. So here we have basically electrons. And then again, what we have is we have nuclear repulsion. So we can see here the overall term is positive, and here what we have is, again, this term is the nuclear repulsion. So this is also representing the nuclei of this molecule. And then we have this term. So this is our repulsion due to the nuclei present in the molecule. And then we have this term, and in this term, this is the repulsion between the electrons in the given molecule. So this is again the representative of the repulsion. And finally, we have the last term here. What it does is it represents the electron and nuclear attraction. So there exists an overall attraction between the nucleuses and the electrons that are present in this molecule, the molecule that we have considered. Now, what is the important motivation here is that the motivation is behind the Bohm-Oppenheimer approximation. And what is that? It is that the nuclei that we have here, these nuclei are much heavier than the electrons that are present in the molecule. And we better understand that the mass of a proton is, talking precisely, it is 1848 times greater than that of the mass of the electron. So at any given instant of time, the electron will feel a Hamiltonian. These electrons, it will feel a Hamiltonian that depends on the position of the nucleus at that very instant. So if I write down this electronic Hamiltonian, the Hamiltonian for the electrons, so we can write down this Hamiltonian, say H electron. So treating the nucleus at rest, that will be minus 1 by 2 sigma delta I square plus 1 by 2 sigma zj by rij, and plus 1 by 2 sigma 1 by rij electrons. So this is for electrons here. So this is for nucleuses here, and this is the kinetic energy of electrons here. And and then we will have minus sigma I and j with zj by ri minus rj. Now, the R, the capital R that we have here, it denotes the dependence on the nuclear position as Rj at once. I mean, in the limit that the nucleus, these nuclei are infinitely massive. So the nuclei that we have in the molecule, they are massive, and they're not going to move. And the position Rj in this equation that we have, this position will be fixed. So I can say here that the molecule will be frozen. It will be a frozen kind of situation in some particular configuration, because being these nucleuses massive, they will be at rest, they'll be fixed. So in this case, that these R's can be considered as parameters. These R's cannot be treated as operators. They are a representative of a parameter rather than that of the operators. So, so that defines this effective Hamiltonian for the electrons. So for any fixed configuration, so we have electrons and we have the nucleus. So for this configuration of this molecule, one is interested in solving the Schrodinger's equation that involves only electronic degree of freedom. That would be more precise. So we can think of Hamiltonian as electronic and put down a state of it as psi electronic. R is fixed, and this state will lead us the energy eigenvalues for electronic as R psi of R. This is electronic wave function. So what we have noted here is that we note here what is important here is that the Hamiltonian and its eigenstates and its eigenstates and eigenvalues, they depend particularly they depend on some particular nuclear configuration, where we have assumed that these nucleuses are at rest. So this is a very important element of Oppenheimer approximation. What it does basically is that it allows to compute the electronic structure of molecule without saying anything about the quantum mechanics of the nucleus. So once we have solved the electronic Schrodinger's equation, we can write down the effective Hamiltonian for the nuclei by simply adding back in terms that were left out for this electronic Hamiltonian. So if we write down things in that direction, so suppose we have Hn as the Hamiltonian for the nucleuses, so that will be minus 1 by 2 sigma. Then, okay, they are nucleuses, and this is 1 by mj del j square plus E electronic R. So hence, what we say here is that the nuclei move. They move on an effective potential surface that's defined by the electronic energy, and certainly we can define the wave function for the nuclei alone, that are the eigenfunctions of this Hamiltonian. So if we write down the state of Hamiltonian on psi n, this will lead to 1 by 2 sigma 1 by mj delta j square plus E electronic R psi n. So what is important here is psi n. So will come with the eigenvalues for overall molecule as E psi n. Okay. So we can see the difference here, and we are not treating things completely independent of each other. We are taking in account electronic configuration, electronic energy into the Hamiltonian of the nucleuses that are present inside the molecule. So we can say here, I mean, if I speak about the same thing in another way to think about the Bohm approximation, it's like it is valid whenever this electronic and nuclear wave functions approximately decouple. The point is, they don't decouple completely, approximately decouple. So we can point out here that the states we are using do not treat the nucleus and electrons as independent particles. We are not treating them as completely independent of each other. The parametric dependence of the electronic eigenstates, what they do is they introduce a non-trivial coupling between the two. So the decoupling need not to be complete for this Bohm-Oppenheimer approximation. And finally, what we will like to note about this structure that we have here is that the electronic Schrödinger wave equation can also be derived. We can derive that equation by assuming that the high mass of the nuclear mean that they can be treated. Talking about nucleus here, this nucleus can be treated classically as a classical particle. Then the nuclei are completely described by the trajectories. So they have trajectories in the molecules. And the electronic Hamiltonian that we have written down, which is HEL, can be thought of as depending either or R or on time. And if we take any of the approach, its dependence on R or time, and assume that nuclei move infinitely slowly, we have a Hamiltonian H electronic that is dependent on the time and that is changing very slowly within the time. And hence, if the electrons start out in eigenstate H electronic 0, if they start out from 0, they are going to adiabatically follow the eigenstates along the trajectory and end up in an eigenstate of H electronic at some time as HELT. So we can say that if the nuclei are moving slowly, if we have the nuclei and they are moving slowly, I mean, they can be treated as classical particles. And the electronic Schrödinger equation falls out naturally from this process. Now for this reason, the Bohm-Oppenheimer approximation is sometimes called adiabatic approximation. But at the same time, I would like to reveal that Bohm-Oppenheimer approximation does not treat nucleuses. It does not treat nucleuses classically.